So now we will consider forced harmonic vibration. Forced means, so far we have seen that there was no external force, and here in this topic today we will consider that there is an excitation force of this form. F naught is constant and then sine omega t, where omega is the frequency. So it's a harmonic force, and this is forced harmonic vibration. So far we have seen free vibration where there was no excitation force, and free vibration we have seen undamped and damped. Undamped vibration, actually all vibrations are damped to some extent, but it is important to learn undamped vibration in order to find out the natural frequency, and the natural frequency of undamped vibration, free undamped vibration, is more or less same as the damped natural frequency. So if the damping value is small, so but in this topic is little different, because here now there is an excitation force, and we start with the equation of motion. So if you see the forces, and right, and the downward direction is positive as usual. So here we consider viscous damping. That means damping is proportional to velocity, and the proportionality constant is c, the damping coefficient. So minus kx minus cx dot plus f naught sine omega t is equal to mx double dot, or mx double dot plus cx dot plus kx is equal to f naught sine omega t. So here, since this is viscous damping, this equation is a linear second order equation with constant coefficients. So if you consider the complementary function, then the right hand side has to be taken as 0, x double dot plus cx dot plus kx equal to 0, and that gives you the complementary function, which is the solution for free vibration. But free vibration slowly decays down with time, so it is also important to find out, or it is very much important to find out the particular integral. So actually this particular integral is what we are going to we are trying to find out. So here you can apply the methods which you have seen in your mathematics class for solution of differential equations, but we'll use a simpler technique, which is that we'll just try to convince ourselves that if the right hand side is a harmonic function, then the solution will also be a particular integral is also a harmonic function, because by taking time derivative of this you are getting the right hand side. If the right hand side is not harmonic, then how can you get a harmonic term on the right hand side? Because the left hand side must be equal to the right hand side. But in presence of this, here the phase of the right hand side and the left hand side will not be same. If you take just sine omega t as a solution, then from this term sine omega t will come, from this term sine omega t will come, but cos omega t will come from this side. So simply a sine omega t term you cannot take as solution, you have to take a cos omega t term also, and that means you have to take a solution with a different phase. So here we take the solution as sine omega t minus phi. That means x having an amplitude of capital X, a frequency of omega, and a phase lag of phi compared to the excitation force. Again we since it is simpler to work with exponential functions, we take as x as x to the power e to the power I omega t, remembering that this is actually the imaginary part of this. This is actually the imaginary part of this, and whatever you get from here, and we take f naught as, and the right hand side as, we take the right hand side as f naught e to the power I omega t, or let us make x bar e to the power I omega t, and this as not e to the power I omega t, knowing that the right hand side is actually the imaginary part of this. So whatever we get by putting this here, we will take the imaginary part of this as solution. So here if you put this here, so we get minus omega square mx e to the power I omega t will be common in all terms, so that has to be cancelled out. F naught or x bar is equal to f naught so we have got what is your x bar. Now as you see, the denominator has got one I, so the denominator is complex. That means this right hand side has a magnitude and a phase, and the magnitude of this is the magnitude of x bar, and the phase of this is the phase of x bar. So x bar is not a real number, it is also a complex number. That's why we have taken it as x bar, not as x. So so now see, we can write this as f naught y, the amplitude is this is the amplitude of the denominator, and the angle of denominator is tan inverse c omega y k minus, which means this is f naught, the angle is, this is the amplitude minus tan inverse so this we can take as some x bar is equal to amplitude e to the power minus I phi, or angle as minus phi. That means this is x to the power e to the power I phi, and x e to the power I minus phi. This means actually x e to the power minus I phi, and so, and this actually means, this angle means e to the power minus I tan inverse c omega y k minus m omega square. That's why this is a simpler way of writing it by giving the angle symbol. Actually it means e to the power I, and the angle is minus this. So from here you can equate, that the amplitude is, so x is f naught by and phi is tan inverse c omega by k minus m omega square. So we have got the solution. So this is the amplitude. Then actual, what is the actual x? Actual x is x e to the power minus I phi, which is x bar, and then e to the power I omega t, e to the power I omega t. So this is x e to the power I omega t minus phi, and this x is actually this, and this phi is actually this. So we have got the solution. And here also you see that x is actually of the same frequency omega as the forcing frequency, but it is lagging by an angle phi, and you have to take the imaginary part of it as the solution. So what is the imaginary part of this? The imaginary part of this is x equal to, what is the imaginary part of this? This is cos omega t minus phi plus I sin omega t minus phi. So this is, the imaginary part is sin omega t minus phi. So this is the solution, because you have to take the imaginary part of the solution. Imaginary part you have to take, imaginary part, because that was the condition. Because here you have already taken, you have already assumed that this is the forcing function, and the actual forcing function is the imaginary part of this. So also you have to take the imaginary part of the solution, and this is the imaginary part of the solution, and where capital X is this and phi is this. Now it boils down to, now the job is actually finding out the solution in some non-dimensional form. So x is equal to, so here we just take out k, that means in the denominator we take out k, so this becomes 1, because k in the root k square, again the square is there, so k minus m omega square by k whole square plus c omega by k whole square. So this is f naught by k. So here this is actually 1 is okay, and you know this k by m is actually omega n square. So this is 1 by omega by omega n square, and what is c omega by k? So c is actually, you know, to cc, and this is twice m omega n. So c omega by k is equal to this twice m omega n by k, and here this k by m omega n square. So this is twice this one omega is here of this omega, so this becomes omega by omega n. So this is twice beta omega by omega n square, and again if you take this as your static displacement and you call it x static, then x by x static is equal to 1 by, and if you call this omega by omega n as r, so this is 1 minus r square whole square plus this square. So this is an important relation, and we'll try to understand what is the physical meaning of this relation in our next class. Okay, and another thing is, what about this angle? So angle is this phi equal to tan inverse of this, or tan phi for the phase, and for the phase we know that tan phi is equal to c omega by k minus m omega square. Again you divide by k, so this is c omega by k, and here omega by m omega square by k, so k by m is omega n square, and c omega by k we have already seen, c omega by k is twice xi omega by omega n, so this is twice so again this is so in the next class we will see the interpretation of these relations which we have derived today. So thank you.